Okay, time to get started. So last time we were talking about change of variables, you recall. And remember, the big idea is that we're generalizing the substitution rule appropriately interpreted, right? So the substitution rule is this right here. And the big reinterpretation, the point of view that tends not to be presented in single variable calculus classes is that, for one thing, when the function goes one direction, expressions go the other direction. This is what we call a pullback, right? So this is not a peculiarity of substitutions. I mean, this is kind of a general construction that has natural applications in a lot of areas of math. I'll just say that broadly. So that is one aspect of that, is that we're going backwards through the function. It's important to observe. The other important thing to observe is that when you push a subinterval, let's see, I'll do this in orange. When you push a subinterval forward, it's going to be all distorted, of course, by the g function itself. And in so doing, it's going to be stretched out to become bigger. And we discussed why g prime, right, really should be that stretching factor. That's how much bigger dx is than dt, and therefore why you have to insert this factor of g prime. Now, again, there's different points of view on why should you insert that g prime, but this is the point of view that I want us to go with for our purposes here. So with this all in mind, we said, hey, can we do something along these same lines, but for a multivariable function, right? So here we have a function where there's two variables in and two variables out. And in that scenario, well, I mean, an expression on the right will still pull back in the usual way, plugging in still structurally pretty much the same. And then again, there's this question of, by what factor is this little piece of area multiplied to produce that little piece of area? And that stretching factor, right, is another sort of, just like in the single variable case, another factor that has to be inserted when you do that pullback. Okay, so this is about where we left it. I guess the last thing that I did is write down the formula for the stretching factor, and it's the absolute value of the Jacobian determinant. Keep in mind, the word Jacobian is an alternative terminology for the derivative matrix, right? So Jacobian determinant just means the determinant of the derivative matrix. Okay, so the absolute value of the determinant of the derivative matrix is our stretching factor. And then don't forget, we also observed this alternative notation, which is very handy, very convenient in multiple ways. And we're going to see it pay off pretty big today. Okay, so this is about where we were. Hope this all rings bells. And now let's get to actually doing one. Right? Let's get some dirt under our fingernails. So we're interested in the following scenario. We have the unit square in the UV plane. That unit square, I'm going to plug into some function. Let's see here, some function called g, which, by the way, is given right there. There it is. Specifically, we're going to look at the image of the unit square by way of this function. So keep in mind, the word image means what comes out, right? So when you take the unit square, you plug it into this function, what comes out will be a different set, right? What comes out is something kind of like this. All right, that is our domain for an integral. And we want to ask, how would we go about computing this given integral of x plus y over this domain in the xy plane? That is a pretty weird way to define a domain. I'll grant you that, right? But this is a scenario that actually is tailor-made for this method that we outlined on the previous page. This is called change of variables. Okay. So notice the very first thing you have to do if you want to do change of variables, you have some integral defined on some domain. If you want to be able to talk about a pullback, well, you need your domain to actually be the image of a new region that you know what it is, and by way of a function that you know what it is. And luckily, that's how this question was given to us, right? It came to us as that the domain for our integral that we're interested in is literally defined as the image by way of this function, right there, given, right, of this pullback domain, I like to call them sometimes, this unit square, again, given right here in the statement of the question. So, cool, we're all set. And if we want to use change of variables, again, here it is. If I want to use change of variables, all right, well, x and y are some functions of u and v. Plug them in. No big. That's just literally plugging in. Nothing interesting happening here where x and y are functions of u and v. Well, yeah, that's how they're defined. That's just a given. The only little tricky part that remains is don't forget about the stretching factor. It's very easy to make the outrageous mistake of just recopying dx dy and just, I think I'm just going to rewrite that as du dv. And that's garbage nonsense. Of course they're not the same, right? So you've got to insert that stretching factor. And to insert it, you have to compute it. So that's going to be our first step down here, then, is to, given our g function, we have an orange right there, we're going to take the appropriate partials. Notice that our u partials go there, and our v partials go there. Now a little bit of, single variable calculus, partial derivatives, basically single variable. I need a plug and chug to compute those partials. Remember that our what we're interested in is the determinant of that derivative matrix. Right? So we have to compute up that determinant. That gives us this. A little bit of algebra, no big deal. And then last little thing to remember, real easy to forget, last thing to remember is that what we're actually interested in for our stretching factor is specifically the absolute value of that Jacobian determinant. So looking at this expression, here's where we're going to have to pause and kind of recollect, reevaluate our situation. How do I decide how to take the absolute value of this thing? So I can do it like this. How do I take the absolute value of 4uv minus 9? Now, your first instinct might be to, I don't just stick it into the integral, let the integral deal with it. Integrals, you may recall, can't deal with it. We don't have formulas for how to compute antiderivatives of expressions that have absolute values in them. It's just, it doesn't work that way. So we're going to have to figure this out. Right, we're going to have to work this through. So how do we make those absolute values disappear? Related question, basically the same question. How do I decide when this thing on the inside here, how do I know if it's positive or negative? Or worse, when or where it is positive or negative, right? This is a thinker. This is not a plug and chug kind of situation. This is something where you have to pause, look at, remind yourself of the big picture, right? Take stock and then think it through. So here's the big picture. Keep in mind we're doing this pullback. Keep in mind that this is the u-axis, that's the v-axis. Our new integral is going to be defined on this unit square in the UV plane, which means that as I compute my pullback integral, u and v will always come from this unit square. Yeah. Which means very conveniently that you can see it right here, u is always going to be between 0 and 1. And analogously, v is always, you can see it right here in the diagram, v is always going to be also between 0 and 1, right? So having made this observation, and again, the diagram, I'm a big fan of having a representative diagram. the diagram is what tells us. I can look at my pullback domain and just straight up see it right here in the picture. Look, check it out. U always between 0 and 1. V always between 0 and 1. And that makes the rest of this question easy, because if U and V are between 0 and 1, then this expression right here inside of the absolute values is never bigger than -5, which means it's always negative. And if it's negative, the absolute value of something that's negative is always the negative of that negative expression, right? So this absolute value turns into that. How we doing? Everybody okay? Common landmine to step on. Please do not make the mistake of thinking that the absolute value of a sum of two terms is equal to the sum of the individual absolute values. That is absolutely not true, and at a basic level, right? So that is just not how absolute values work. So you really do have to look at the whole expression. Okay, so we're in business. This is the integral that we were asked to compute. We're going to start plugging stuff in. X, what am I going to do with that? What is X? Well, it says so right here. X is that expression, which I then pop right in there where the X was. Yeah. And then let's see, Y. What is Y? Well, okay, it says right here that's the formula for Y, and we pop that in right where the Y goes. That's just how, I didn't do anything, right? That's just plugging in the givens for how our change of variables function is giving us X and Y as explicitly known functions of U and V. Plugging in. The only real tricky part in the pulling back process is don't forget to put in your stretching factor that we've just carefully computed right there. Yeah.
So, are we expected to find GUV, or is it something we're always going to be given?
That's a great question. No, there's no alwayses. Yeah, there's a whole question of how, in general, do we find those functions. So sometimes they'll be given. Sometimes you will make clever choices based on some specifics of the question, and I'm going to show you some examples of how to make such clever choices. Right? So I'm not going to ask you to reinvent the wheel on that, right? But I am going to show you how the wheel works and ask you to use, right? So you will have certain examples to kind of mimic, and sometimes it'll be straight up given, and then certain occasions it will be that there is there are some standard choices that get used a lot. That sometimes you can just look and see, hey, what about one of my standard choices? Is this going to help? Right? So yeah, it's a long, complicated question. Yeah. Okay. All right. So, yeah, we have made the transition. Now, let's decide if this was worth it or not, right? On the one hand, we started off with this integral defined on this domain. And now, instead, we have successfully turned that into this integral defined on this domain. And which one do we like better? And let's think carefully on this now. This original integral has a fantastically convenient integrand. It's just x plus y. Gotta love it. Super nice, right? My new integrand, not so nice. It's cubic. No, quartic. Excuse me, quartic. Right? So, almost being equal, I like the original integrand better. And that's a distraction. That is not the point. Far more important than little quibbles about how, antipartials involve fractions when I have a, higher order polynomial. Yeah, that's not the problem. The problem is the domain. You look at this domain, corners everywhere. No matter which direction you slice, you're going to hit two separate corners. That's a pain. Right? Note worse, I don't really even have the equations for these curves. I kind of have sort of a parameterization of sorts, right? From the fact that they're images of other curves. I guess I could parameterize them, but how to find the equations of the curves that will determine your bounds, that's an issue, right? So this is a nightmare of an integral. And we have now successfully turned it into an integral. Okay, it's, there's going to be there's multiple terms, and there's going to be some fractions, but look at my domain. Everyone's favorite domain for a double integral, right? 0 to 1, 0 to 1. Hard to beat that for easy. This is much more desirable. So this is a big win. Does everybody see how this is a massive victory? Okay. So, yeah, cool. So here's some, I don't want to call them standard exactly, but here are some change of variables functions that can be useful sometimes. Translations, stretches and squishes in various different directions, rotations, these kinds of things pretty regularly can turn, no pun intended, can convert undesirable domains into less undesirable domains. We're going to see an example in just a minute. I just want to point out that don't forget, easy to forget, and come back up here to the original thing here, right? Whatever your function does, when you do the pullback, you're literally going backwards through that function. So what happens to your domain is in some sense the opposite of what your change of variables function does. So let's see that in action here. Here we go. So new domain. Here we go. Our domain is this square with various corners given, which you can plot and do a little geometry and persuade yourself is this square right here. By the way, that's a nice little exercise. Persuade yourself that these four corners actually do make a square. I encourage you to use some vector algebra on that, right? And maybe a dot product somewhere in there. Anyway, think that through and make sure you can persuade yourself that this is literally a square. All right, so on that domain, we want to compute this integral that doesn't look scary at quick glance because the integrand looks really nice, right? But again, it's not about the integrand. It's about the domain. You look at our domain. This is a pretty ugly domain. Corners. This is 3 separate integrals, right? Not desirable. Bummer. Okay, now I will point out that I can view this as being the result of doing a counterclockwise rotation, right? So I'm going to imagine a counterclockwise rotation like so, right? And if I were to think about this square here that has the same side length, if you take that green square and if you do what this change of variables function t says, namely a counterclockwise rotation, the result of that counterclockwise rotation is, in fact, to produce our given square. So that means when you pull back, right, in some sense the exact opposite happens. The change of variables function rotates something counterclockwise. The result of pulling back means that I will take this already rotated square and I will be effectively rotating it clockwise when I say I'm going to use this as my pullback domain instead. Right? So the change of variables function itself is counterclockwise, and as I transition backwards, I'm effectively rotating my given domain clockwise. So there's always this oppositeness when you're doing change of variables functions because of the pullback aspect of things. So, keep that in mind. Okay, and with that noted, how do we represent a counterclockwise rotation? And y'all are going to recall this is one of the linear algebra tricks that I pointed out at the very start of class is something I'm going to assume that y'all are proficient with. So if your linear algebra is maybe a little, it was a long time ago, or if you've kind of forgotten, or if you were never really quite super comfortable with it in the first place, take the time as needed. Come to office hours. Happy to help. Right? Please come to office hours. I'll totally show you how to do this. And the big idea is it's a linear transformation. Whoops, purple. It's a linear transformation, therefore represented by a matrix. And I claim that this is the matrix by thinking about how the columns are the images of the standard basis vectors. So again, details to be worked out there. Make sure you're either good with that or that you follow up with me in office hours or with the other instructors or with other resources. But make sure you can do that. Okay. The angle here, being pi over 6, makes these numbers work out like that. Okay. All right, so we're in business. We have ourselves a change of variables function. We can compute our stretching factor. Here's our formula for our stretching factor. It's Jacobian determinant. Oh, I am going to have to take the absolute value. Get to that in a minute. But our Jacobian determinant, take this formula here, take the various partials. There's your derivative matrix. We take the determinant of that, and as the arithmetic works out, we get 1 as our stretching factor. And what are the odds that a formula that involves trig and square roots and fractions and, oh my gosh, all this stuff, and then the stretching factor is exactly 1? Seemingly a lucky, weird coincidence. Let me try to persuade you there's nothing weird about this at all. This is highly expected. We are, in fact, doing a rotation. And when you do a rotation, stuff doesn't get bigger, right? Rotations are rigid motions. They don't change how big things are. So keeping in mind that this thing here that we just computed, its job is to represent how much areas get stretched out. If they don't get stretched out, then that factor, of course, should be 1. Is that geometrically believable? Okay. Excuse me. That said, point of order for the course, even in a situation where you might be able to make a geometric argument, I do still want to see the calculation. So think of this not as an alternative, right? Think of this as a plausibility argument, right? And it's kind of good to know what you're supposed to be getting to. It makes you feel more comfortable when you get there. And that's all. Okay, and kind of off we go at this point. So again, our original integral was this, and now let's plug in. The plugging in is the easy part. X. What am I going to do with that x? There's the formula for x. X is this dot product. And so, plug it in. Right? Likewise, y. What am I going to do with this y right there? Well, okay, y is that dot product. So, y, we just plug it in. So the plug it in part, again, that's the easy part. It's just a matter of identifying what is, in fact, your formulas for your change of variables function. Just kind of stick them in there, right? The tricky part is to make sure to remember to insert the absolute value of the Jacobian determinant. So absolute value of 1, of course, it's just 1. And now we've successfully done our change of variables. And our old integral on that domain that we were not happy about, right? This integral on this undesirable domain, I've now rewritten that as an integral on my new pullback domain, and check out how awesome those bounds are. It's, I suppose if I wanted to get ultra quibbly, I could bemoan the fact that these are 2s instead of 1s, right? But that's, not a problem, really. This is a much nicer domain. It's just a rectangle. Okay, my integrand's got some weird constants in it. No big deal. They're just constants. This is a massive win. We've just cut our workload by a factor of 3. because what would have been 3 separate integrals is now merely 1. What do you think? Everybody with me? Okay. Okay, so a couple of little formalities that have to get said in order for what I'm showing you to actually work. Technically, you need your change of variables function to be continuously differentiable. We're not going to encounter any situations where that's going to be remotely a problem. So anyway, there is that. Then technically as well, and this was a little subtle one, but it's got to be invertible. Weird things can happen if the function's not invertible. Then the idea that, when you push it forward, then you can just pull it back, but not really, because it's not invertible. The one-to-oneness of it all gets messed up. So issues can arise. So you do need to make sure that your change of variables functions are invertible. Again, that's not going to be a problem for us. Okay, so here's a related trick. Let's think about what would happen if our change of variables function goes the other way. Hypothetically. Okay, so what do we know? We know that if x and y, that's a bad color. We know that if x and y are functions of u and v, then that's our stretching factor. How do we know this? Well, the rule is output variables, we take their partials with respect to the input variables, and Jacobian determinant, absolute value, all that business. Okay. Right, fine. Okay. What if I imagine the function going the other way? What if I have u and v written as functions of x and y? Well, the same basic idea applies if my change of variables function is going the other way, and we'll see in a minute why we would want to, why that's natural. But u and v now are our outputs. U and v, therefore, are what we're taking partials of with respect to what are now the inputs at this point now, x and y. Right? So, so when it turns around, you take the partials of the other variables with respect to the other variables. Now, question comes up then, what is the relationship between these two different stretching factors? And I make the case that, well, of course they have to be reciprocals of each other. And not because they look like it. Not because we write this as a fraction. Right? Keep in mind, this was a kind of a made-up notational choice. This is not a fraction. Right? Let's look back where it came from. Here's where we decided to use this notation. I just decided to rewrite with that notation what is in fact a determinant. Well, an absolute value. But anyway, determinant. It's not a fraction. We draw it as a fraction because at least in this sense over here it behaves like a fraction, but it remains that was kind of wishful thinking and it's not really true. So that's not why these are reciprocals of each other. The reason these are reciprocals of each other is because if I take a little piece of area over here, and if I look at its image, whatever that image is, I don't know, some wacky, right? And then if I go back the other direction, whoops, wrong color. Go back the other direction. After all, these functions have to be invertible. Whatever I put in, if I go over and then come back, I get the exact same thing. So doing the one stretching factor and then subsequently doing the other stretching factor results in nothing happening, right? So the blue stretching factor followed by the orange stretching factor results in nothing happened, and therefore a factor of 1, and therefore these are reciprocals of each other. So this is not true because of the appearance of being fractions. Quite the opposite. It makes sense to write these as fractions because they behave like fractions. at least now in this second sense that we're seeing here. Okay, so cool. We like it when stuff works out. Let's see this in action here. Here we go. This is going to look like a weird example. It's going to look like I manufactured a deliberately awkward, just to be awkward example. This is not the case. I want to be clear where this example came from. This came from an application in thermodynamics. It's not exactly precisely the thermo situation, but if and when those of you who are engineers take a thermodynamics class, you're going to see a region that looks a lot like this, over which you're going to need to compute some integrals. So this is very real world natural. This arises naturally in applications. So now I've cleaned up the numbers, and I've cleaned up a bunch of extraneous stuff that we're not yet able to deal with, and we're not going to do any thermodynamics in this class. But this weird scenario where I have these two curves and then these two curves. And if I look at this little thin kind of, whatever you'd call that oddball shape right there, that's kind of in between. If I need to do an integral on this, which again, I claim it's going to happen, right? That's a thing. When you need to do an integral on that domain, notice you have yourself an ugly domain. We've talked about this before, but this shaded region here, if I think about how I would slice that up, well, as I slice, starting at that point, slices move along until I hit that corner, at which point things change. And so I have a totally new integral as I slice beyond that point until I get to this corner, at which point the shape of the domain changes in yet a different way, and I have then yet a third integral before I get to the end. And likewise, if you slice it in the other direction. So this is another one of these super annoying multiple chunks if you come straight at it. Okay. Okay, here's the trick. I did not think of this trick. Somebody showed me. Don't make the mistake that I did when I was y'all's age learning this for the first time, and I thought, man, I never would have thought of that. Yeah, you're not supposed to have thought of this in the first place, right? Most people didn't. Most people haven't. Most people probably wouldn't. Your job is to see the trick, notice how the trick works, and then be able to capitalize on it with the benefit of having seen it done already, right? So don't get intimidated by how clever this is, like I did. Okay, so here's the trick. If you have wrong stylus thing. If you have one set of equations describing a couple of curves and another set of equations describing another couple of curves, make sure that those equations are written as level sets. Right? Stuff equals constant. That's a real big part of this. Make sure they're written as level sets. Stuff equals constant. If it's not written in that form, write it in that form. Right? Get it into a form where it is level sets. Then, having written them as level sets, you can take the first function of x and y, call that u. You can take the second function of x and y, call that v. Notice we now have a function from the xy plane to the uv plane. X and y are now inputs, not outputs. U and v are now outputs, not inputs. Our change of variables function is going backwards, but these curves become super easy to deal with. Let's walk through them. What do I do with this curve right here? That curve has the equation xy equals 1. How do I what is the image of that curve over here in the UV plane? Oh, well, that's actually pretty easy because xy, after all, is just u, which means that curve turns simply into u equals 1. xy is, after all, just u. So, boom. So, curve turns into a straight line. And likewise for the other 4. And so the really nice effect then is that this weird collection of strange curves intersecting in undesirable ways in the xy plane, that turns into a rectangle in the UV plane. It's awesome. Everybody see the move? Okay. Really, really nice. Cool, so let's compute our stretching factor. We notice have u's and v's as functions of x and y, so we take our partials with respect to x, we take our partials with respect to y. Again, make sure you're good with the partials, make sure you're good with the structure of the derivative matrix, make sure you don't accidentally transpose it, that's a problem, right? So be careful, but no big. Easy to compute our Jacobian determinant, and we have that is the stretching factor for that function. Everybody okay so far? Okay, now here's where, a little bit annoying, a little bit awkward. I want this to be a pullback. I want that pullback to go that way, which means I really need for my change of variables function to be going the other way, but it isn't, and so everything's backwards. Okay. Well, conveniently, nice handy dandy little formula right here that says if you have computed the stretching factor going the wrong direction, no sweat. Just take a reciprocal of it. That will give you the stretching factor going the way you want it. Super convenient. So here we go, right there. The wrong stretching factor is that, and that means that the right stretching factor is this. Everybody good? By the way, the algebra works out really nicely on this, and I, again, credit the notation. Quick reminder, here's what we started with. This is the integral that we wanted to compute. And notice I need to rewrite dx dy. Here's my rewrite of dx dy, and again, notice the little... It's like there's a cancellation. There isn't. This is not a fraction, right? But it's as if, we like the fractional notation because, man, it really looks like those ought to kind of cancel. And this little notational illusion will always point you in the right direction. It's doing some paperwork. It's doing some bookkeeping for you. And I love it when notation can keep us on track. It's very handy, right? So it's as if these cancel and thus give us the dx dy. And that's a real easy way, by the way, to remember, wait a minute, which way should it go? Which way do I want partial xy, partial uv, or do I want partial uv, partial xy? Wait, which one did I compute? Which one do I need? Are they the same? Let this keep track for you. Okay. So yeah, the partial that I got after, the stretching factor that I got after taking the reciprocal is the one that I need. Thus that. Okay, now, last remaining annoyance in this example. When you plug in your stretching factor, notice that even though you've done the pullback, even though we're now working off of our new domain, we're in the UV plane, our domain is a rectangle, life is good. The one little annoyance is I have not yet been able to plug in. All right, I don't know what x is. I don't know what y is. Look at our change of variables function. It's going the wrong way, and therefore I don't have formulas for x and y explicitly. So, what do? How do I rewrite this in terms of u and v in order to work out the uv integral that, of course, I want to do? This is another catch as catch can, by hook or by crook kind of a situation. There is no single method for this. I'm going to show you a method that works here. Analogous tricks will work in analogous situations. I look at the expression that I have, and I think to myself, all right, that's a product of powers of x and y. Wait a minute, what do I need it in terms of? I need my answer in terms of a product of powers of x and y and another product of powers of x and y. Okay, now let's just think out loud for a second. If I wanted to find a relationship between products of powers of x and y, and I wanted to do something to those to turn it into a different product of powers of x and y, I propose that the reasonable guess would be to take a product of powers of those products of powers, because I know at least that will produce a product of powers, and hopefully I can tweak the a and the b to figure out how to make this work. So, short version, guess. Right? But guess based on the structure of what you have and what you want to achieve, and then speculate algebraically how do you expect those things to relate. So, for example, I mean, just to be silly here, I mean, if I'm looking at this product of powers and this product of powers, and I want to produce that product of powers, it would be silly to speculate about the possibility that cotangent might be helpful, right? I mean, it's what are the odds? It really doesn't look like cotangent's going to help here. Cotangent's not going to help me turn green and blue into purple. But I could imagine that something like this might. So it's a guess, educated guess, you might call it. And then it's just a matter of kind of multiplying everything out and writing things down. You multiply this out, you get that, which means that. And so therefore the powers of x have to be equal. And therefore the powers of y have to be equal. And then you've got yourself a little bit of linear algebra that you can crank through, and there's your A and your B, and that gives you your expression that you need. Is that cool? All right. I can't say that it'll always be like this. It's this is just how it worked in this situation, but make a good guess, and then work out your details. Okay. All right. So now y'all will recall when it came time to ask what the formula was for the stretching factor, I kind of punted and I said, we've got a lot going on here. We're thinking about domains and pullbacks and stretching factors, and there's a lot of there's just so many moving parts, and I didn't want to get distracted into the where did this come from. So I do want to show you in just the broadest of brush strokes, where this formula comes from for the stretching factor. The big idea, keep in mind, its job is to help us figure out by what factor do you have to multiply this area to get this area, right? The area of its image. How much bigger is it? That multiplicative factor we're going to compute by just straight up computing that area. And we're going to find, as you see here already on the page, that it will come out as being explicitly a multiple of that area. And you can see the answer happening right here. It is. There's my, wrong color. Here is my stretching factor formula being exactly what it's supposed to be. So y'all can see this calculation is going to give us our formula. Right? So let's see the broad brushstrokes of this calculation. As I'm trying to compute this area on the right, I need to understand that vector. That's just the image of this vector. And the way you relate input changes to output changes is by the derivative matrix. There's our derivative matrix right there. That's what we do to the input vector to get the output vector. If I want to compute this area, then Chapter 1 tells us that the one of the edge vectors for our parallelogram is our first column, and the other one is our second column, and then we take the determinant, and then we take the absolute value. That's just Chapter 1. And then you manipulate the algebra around, and we get our desired result. So it's really pretty straightforward. It's just it's tricky because I'm using an interpretation of the derivative matrix. I'm flashing back to an old formula about areas of parallelograms in 2 dimensions, and then again some linear algebra about how do determinants vary when you multiply a column by a scalar factor. And there's a couple of little finer points in there you can think through, but that's the broad brushstrokes of it. Okay. 3 dimensions. Everything we've done so far has been 2 dimensions. What if it's a 3-dimensional domain? Good news, practically identical. Almost exactly the same. Because, same sort of reasoning, right? If you have a change of variables function, and if you have a domain that is an image, yikes, this is a weird shape. If that domain is an image, then you can just talk about doing a pullback. All right, you can pull back just like we did in 2 dimensions. Plugging in is plugging in, no tricky curves there. The only tricky bit is the stretching factor, and I'm just going to assert and leave as an exercise for y'all to think through that stretching factor, again, is the absolute value of the Jacobian determinant. It's the same. It's the argument is a lot like this, just 3-dimensional instead of 2-dimensional. Very, very analogous argument. So, punchline. You can do change of variables in any dimension. Your stretching factor will always be the absolute value of the Jacobian determinant. Have fun. Okay, so I have an example here, which we are not going to finish. Let's see how we're doing on time specifically. All right, well, we can do just a little bit more. As a segue into this example, I want to point out this theorem. This is an easy thing for y'all to confirm for yourselves, but it's a very valuable punchline. Whenever you use a linear transformation as a change of variables function, and keep in mind, linear transformations can always be represented by matrices like so, right? That's one of our handful of big takeaways from linear algebra that we need for this class, is that linear transformations are represented by matrices. Right? If that's the case, then the derivative transformation for that linear transformation, the derivative transformation is just the matrix itself. This is easy to check. Just I'm not going to ask you to prove it rigorously or in general, but write down a 2x2 matrix of constants. Write down the corresponding linear transformation. Take the appropriate partials, and you will find, hey, son of a gun, look at that. The derivative matrix is exactly the matrix representing the transformation. It's a neat fact to know. And you know what? This is close enough. Let's go ahead and just call it a day right there. We will pick up with this last example next time. See y'all later. Hope everybody had a good weekend.
What?